we go. So question 7 on January 2013, and it doesn't look like it at first, but it's a big, big question about differentiation. What we're looking for is this trigger in here, that bit there, where it says find the coordinates of the minimum point. Even though it didn't say find dy by dx or differentiate or find f dash of x, that's the clue. When we read that, we know that means we're going to have to differentiate. And there's a lot to do with this. Before we can differentiate it, we need to get it in that term by term form. So the first job to do with this is actually going to be to multiply out the brackets. And again, this is going right back, you know, that the first thing that I said that in the polynomials is about multiplying brackets and adding and subtracting things. And here it is appearing tucked away inside a much bigger question. If you feel that you're happy just to kind of go with all the lines all over the place and multiplying everything out and do all of that, then go for it that way. Just to be super careful, I might be inclined to take an extra step. Because you know, even if this was just multiplying out this on its own, I'd want to do it right. But multiplying this out, and then I'm going to differentiate it, and then I'm going to try and find stationary points from that I really can't afford to make a mistake in doing this. This has got to be right. So I'm going to be extra careful that I'm doing this perfectly. And then collecting together all the right terms. What have we got? X cubed minus x squared, and then minus x, and then plus 10. And really, you know, we've got to get that right, because so much depends on it later on. And you will get method marks, but you're going to lose so many accuracy marks if you make a mistake in that. Right, coordinates of the minimum point. Minimum points happen when dy by dx equals 0. So there is our pointer. That's why. Let's find dy by dx. By differentiating it, 3x squared minus 2x minus 1. We've just talked about this. Stationary points, minimum points, maximum points happen when dy by dx equals 0. So we now need to say what happens when dy by dx is equal to 0. So this, we need to factorise this. That would be 3x squared minus 2x minus 1 is 0. And I want you to actually really state this line here. There's a tendency sometimes, again, for people to find dy by dx, to factorise it, to say, therefore, this stuff happens, without ever actually mentioning that they're putting it equal to 0. But make sure you state that clearly, that you're putting dy by dx equal to 0. We can factorise this. We can either do it with that method we did a little while ago, but actually it starts and ends with prime numbers, so we're going to write it. It must be 3x and x. It must be 1 and 1. We just need to work out the signs that make that work. I think that would be a minus sign there, and that would be a plus. Minus 3x plus x is minus 2x, and minus 1 there. So we've got x equals minus a third, and x equals 1. Out of this, the question said find the coordinates of the minimum point, justifying that it is a minimum. This is a cubic equation, isn't it? And a cubic equation, we know a cubic equation does that kind of shape, or maybe it does it the other way around, but it has a minimum and a maximum in there. One of these would be a minimum, the other one would be a maximum. We could just find the y-coordinate and take the one that's the smallest, because that would be the minimum. But the bit where it says justifying that it is a minimum, they're looking for us doing a bit more than just doing that. So we need to find the second derivative and do that bit. So let's differentiate it again. So d2y by dx squared would be, we differentiate this again, we're going to get 6x minus 2. If it's a minimum, we want the one where d2y by dx squared is greater than 0, because that's what you get for the minimum. So let's sub these values in. I know, in my head, I know that what's going to happen with this, but we'll sub them in anyway, and then we've made sure we've been absolutely clear of it. That, well, 6 times minus a third is minus 2, take away another 2, well, I put a bracket there, is negative 4. Negative 4 is less than 0, so that point is a maximum. That's not the minimum that we were looking for. If x equals 1, then we get 6 times 1 minus 2. I've got that bracket in there again. Which is plus 4, which is bigger than 0, so that is the minimum. And that's it, we've justified that the point that we found to be a minimum is a minimum now. But we need to find the coordinates. It did say find the coordinates, so we need to find the y value that goes with it. And we could use either version, couldn't we? The original equation or our multiplied out version. Doesn't really matter, does it? Subbing 1, we've got 1 plus 2 there, and then we've got 1 squared. What was the equation? Minus 3 plus 5, so we're doing 3 times 3. So we get 9. So we have a minimum at the point 1, 9. Okay. Calculate the discriminant of x squared minus 3x plus 5. There's a little thought going on here, isn't there? This minimum point, the y value, was positive. You remember that curve I drew a little while ago? A minimum point with a positive y value means that turning point up there must be above the axis, mustn't it? Which means that it must only cross the axis once. Which means that when we look at the discriminant of the quadratic bit, that's going to be negative. And if it's not negative, we've done something wrong. So part 2 asks us to calculate the discriminant of x squared minus 3x x plus 5. And that would be b squared minus 4ac would be minus 3 squared minus 4 times 1 times 5. We get 9 minus 20, so we get negative 11. Is this okay? Is this making some sense here? Because what we got was a cubic equation that we just found it had a minimum point at the point 1, 9. If that's 1, 9, that means the x-axis is down here somewhere, doesn't it? The other turning point we had at minus a third, so that's there. So the other axis goes through there somewhere. And we also, if we look back at the original equation, x plus 2 brackets, so that point is minus 2, that point over there. And so this is right, isn't it? We've got the one root at minus 2, the discriminant was negative, so we haven't got the other root happening. This is all, well, this is all actually going to be quite useful in part 3. Part 3 says, explain why x plus 2 times x squared minus 3x plus 5 is always positive for x greater than minus 2. The graph would probably do it, and that's a good sketch of the graph, so we've got that there. But if we want to explain this in some words, well, what we're saying here is that x equals minus 2 is the only real root. That's what part 2 tells us. So part 2 tells us that x equals -2 is the only real root. Okay? The minimum point, the y value of the minimum point is greater than 0 as well, isn't it? The minimum point at x equals 1 has a y value greater than 0. So it crosses at -2. It then does come back towards the axis, but then it turns back and goes up again, and it's always greater than 0 for all those values. So therefore, x plus 2, x squared minus 3x plus 5 must be greater than 0 for all x greater than -2. I think that kind of does it. If I were doing this, I would definitely put the graph that's there in my answer as well, just a little sketch of what's going on. That was a 12-mark question we've just done. Give it a go. Thank you.